In this video, I'll be going through question 16 from the 2014 exam. We're interested in certain properties of the given payoff matrix. You'll have to utilize the simplex algorithm for this question. I'm going to assume you're familiar enough with the simplex algorithm that I don't have to explain all the working details. If you need further assistance on that, check out some of the earlier questions on the exam. I've provided a couple of links in the description. The first thing we want to do here is normalize our payoff matrix so that all the entries are non-negative. To do this, we find the most negative number in the table and add the absolute value to everything. Here, our most negative entry is -3, and so we add 3 to every entry in the table. The next thing to do is understand the linear programming problem we need to solve. To find the optimal mix strategy for player 1, we need to solve the following problem. We will maximize U1 plus U2, subject to the constraints (3, 0, 1, and 8) times U1, U2 less than or equal to 1, 1. Notice that the matrix on the left consists of values from the payoff matrix plus 3, and we use two variables U1 and U2 because player 2 has 2 moves available. We can now write down our initial tableau. We have two slack variables S1 and S2 for our constraints. We include our matrix as per usual, then the identity matrix, our resource coefficients, and the coefficients of the profit function. Now we want to find the entering and departing basic variable. In general, we choose our entering variable by selecting the most negative entry from the bottom row. All of our negative entries are the same, so we can choose whichever one we like. I'm going to choose U2 because there's already a 0 in that column, and it seems like it'll make things easier to work with. To choose our departing basic variable, we'll consider the ratios of resource coefficients to the values in the column of the entering basic variable, provided that the entries in that column are positive. Since there's only one positive value in the column for U2, we don't have to do any work, and we know straight away that this is our pivot. Make sure that when you do this question, you clearly indicate the pivot point. So, moving on, S2 departs and U2 enters. S1 will stay the same. We're going to make this pivot into a 1 by dividing everything by 8. So 1 on 8, 1, 0, 1 on 8, and 1 on 8. And then we want to make everything else in this column a 0. This was already a 0, so nothing has to be changed. And we've got a -1 in this previous row, so we're going to add one copy of the new row 2 to that row. So -1 plus 1 on 8 is -7 on 8. You get a 0 here, 0 plus 0 is 0, and 0 plus 1 on 8 is 1 on 8, 0 plus 1 on 8 is 1 on 8. We're left with one negative value in the bottom row, so our pivot will be in this column for U1. The ratios we're interested in are 1 on 3, and 1 on 8 on 1 on 8, which is just 1. Since 1 on 3 is the smallest of the two, this will be our pivot. So S1 departs and U1 enters. U2 stays the same. We divide everything in this row by 3 to make that pivot into a 1. Now we want to make everything else in this column into a 0. So to make this 1 on 8 into a 0, we'll subtract 1/8 of the new row 1 from row 2. So this becomes 0. 1 minus 0 is 1. 0 minus 1 on 3 times 1 on 8 is minus 1 on 24. Now here we have 1 on 8 minus 0, which is 1 on 8. And then here we have 1 on 8 minus 1 on 8 times 1 on 3, which is 3 minus 1 on 24. So 2 on 24 is 1 on 12. Finally, we want to make this one here a 0, so we add 7/8 of the first row. So this becomes 0, we get 0 plus 0 is 0. 0 plus 7 on 8 times 1 on 3 is 7 on 24. 1 on 8 plus 0 is 1 on 8. And then we have 1 on 8 plus 7 on 8 times 1 on 3. Which is 10 on 24, so 5 on 12. There are no more negative entries here, so we've finished the algorithm. Thus, our solution is given by the values in the right-hand column here. That is to say, U1 is 1 on 3, and U2 is 1 on 12. We will use this to specify the optimal strategy for player 2. To find the optimal strategy for player 1, we need the values for S1 and S2, which are taken from here. That is, S1 is 7 on 24, and S2 is 1 on 8. We also need to know S1 plus S2, which is the value of the optimal solution we've just found. Now we can use this to determine the optimal mix strategy for player 1. The strategy for player 1 is the points P1 and P2, where P1 is S1 on S1 plus S2, and P2 is S2 on S1 plus S2. So calculating this, it's 7 on 24 over 5 on 12 and 1 on 8 over 5 on 12, which is 7 on 10 and 3 on 10. We'll do part C here as well. The strategy for player 2 follows the same formula, except we use U instead of S. So Q1 and Q2 is 1 on 3 over 5 on 12 and 1 on 12 over 5 on 12. I should note here that the optimal solution to this problem is the same as the optimal solution to the dual problem, and the optimal solution to this problem was U1 plus U2. The dual problem corresponds to S1, S2. The point here is that S1 plus S2 is exactly the same as U1 plus U2. So, moving on, this is 4 on 5 and 1 on 5. For part B, you take the reciprocal of the optimal solution and then subtract the value we added at the very beginning. So the expected payoff for player 1 is 12 on 5 minus 3, which is what we subtracted at the start. And that's equal to minus 3 on 5. Now we can use this to answer part D. It's just a matter of checking whether the number we just obtained is positive or negative. Since this is a zero-sum game, Whatever player 1 gets is taken away from player 2. And we can see that since player 1 has a negative expected value, player 2 must have a positive expected payoff, and thus the game favours player 2. And we've finished this question.